Hello everyone, I'm glad to be with you this moment and my name is Akinola Yinka. I'm a professor of computational and applied physics and today I will be taking you through an experiment by PHY interactive simulation. The specific experiment of interest is to actually to be able to determine the period of oscillation of a simple pendulum thanks to the University of Colorado and the PHY interactive project in that university. PHY interactive simulation is actually a project uh, that was birthed by the Nobel laureate winner by the name Carl Wieman in the year 2002 after winning Nobel laureate prize in 2001. Thanks to him for that wonderful concept and initiative that has benefited millions of people globally. Now, quickly, let's look at the aims of what lies ahead of us. The first thing is one to be able to practice accurate time recording, and number two is to be able to show how deduction may be made from observations and graphs. The apparatus of interest or the tools of interest is the PHY interactive simulation, which is accessible at the phet.colorado.edu/en standing for English /simulation/pendulum-lab. So the PHET interactive simulation for this experiment is available on that link. It can be accessed freely. Thanks to Carl Wieman for that initiative. Now, as a form of quick introduction, what is a pendulum? A simple pendulum can actually be described as a small bulb, as you can see from this figure, consisting of a bulb that is suspended from a rigid support, as you can see on the screen, and is suspended using a cord or string or a rod of negligible mass from these rigid supports. And so the assumption is that the mass of this pendulum is actually concentrated at the center of this pendulum bulb. This is a pendulum bulb, and the assumption is that the mass is concentrated here. And we assume that this string or cord has a negligible mass. Okay, so let's quickly dive into the theory behind this simple pendulum. One of the assumptions that comes to mind is that to be able to know the period of oscillation of a simple pendulum. By the way, what is period of oscillation? That is usually denoted by capital letter T. Is simply the time taken for this pendulum bulb to move from here, coming to this other end, and then come back here. And we define it that the period of oscillation is the time taken for the pendulum to complete one oscillation. That is, the time it takes to start its journey from a point and come back to that same point. That is referred to as period of oscillation. And so we are looking at what are the likely things that may affect this period of oscillation. The first thing we look at is the length of the pendulum. If this length is so long, what effect does it have on the period of oscillation? We intend to establish that one by experiment. Then what about the mass of the pendulum? If we have a smaller mass here or bigger mass, how does it affect the time it takes for this pendulum to complete one oscillation? Then the angle of swing is another factor that can also contribute to that. So then lastly, we look at the surrounding medium. If this experiment is taking place in the air, in the water, or in other planets, does it also have effect on the period of oscillation? But for the purpose of this experiment, we are limiting we're narrowing down to just number one and number two. That is, we want to do an experiment to be able to check if the period of oscillation is affected by length of the pendulum, and then we also want to verify whether the mass of the pendulum is a factor that influences the period of oscillation of a simple pendulum. Okay, so let's look at the theory in detail. Based on what we have just said earlier, we just come up with an hypothetical equation, equation 1, that the period of oscillation of the pendulum, capital letter T, is directly proportional to the mass of the pendulum raised to power p. P is considered as an arbitrary number, and then multiply by L raised to power Q, where L is the length of the pendulum, and then a Q is also another arbitrary number. And by simply introducing K as constant of proportionality, equation 1 then becomes equation 2. And then if we are narrowing down to just option 1, which is let's verify the effect of the period of oscillation on just the length of the pendulum only. And so we take off this and we are left with KLQ in equation 3. KL raised to power Q. Now this equation is not linear and we are interested in verifying this using linear equation. And so by taking the log of equation 3, we came up with equation 4. That is, taking the log of t, we gave us log t. Taking the log of k here, we give us log k. And taking the log of L raised to power Q, we give us Q log L. Because between K and L, there's a multiplication sign. That's one we change to addition sign in log. If it's a division sign we have here, that will change to a minus sign when we take the log. Please take note of that. And so comparing this equation 4 with equation of a linear graph, then we can say if we plot the graph of log t on y-axis and we plot the graph of log L on x-axis, then our slope will be q and our log k will be the intercept on y-axis. This is how to assess the PHY sim for this experiment, the Pendulum Lab by the PHY interactive simulation. The full URL is here, as I mentioned earlier, and once this URL is typed into a browser, this page will open as you can see here, and clicking this play button we begin to show the simulation on the browser, and minutes can be used real time online. Another option is to download this particular simulation and have access to it offline. To be able to do that one, there's an arrow here. Once this arrow is clicked, an HTML5 will be downloaded, which can then be used offline on any browser. The offline version can also be downloaded using this link we have here. So this is what the interface looks like. The interface after you have downloaded it either offline or online, this is what you will have for the simulation. Let me quickly take you through some of the controls you have there. Now I've already checked my ruler, so I have access to a ruler to be able to measure the length of pendulum when the need arises. I have the stopwatch which is already displayed to be able to take time for my oscillation. Then to the right here, this is where I will be adjusting the length. This is also where I will be adjusting the mass when the need arises. So for this experiment, we are not touching this part of this simulation window. Okay, so I can simply try to oscillate this pendulum and let's see what it looks like. So if I try to do this, you can see, so the pendulum is oscillating. And to be able to take the time, let's do a quick one. So watch out the time I will click and the time I will start to count. I want to start now. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've taken time for 10 oscillation, and this time will be recorded this way. Usually in the procedure you have to do the recording twice. So for the same length I can take the second time. Okay, so let's go on. Then I can stop what is going on here. Okay, then I can go on to the next slide. Okay, so let's quickly run through the procedures that you need to follow. This experiment has part A1 and part A2 to be done. The first part, which is part A1, this is a procedure that will be followed. Number one, launch FET pendulum lab simulation. I believe that can be done based on the information that have been provided earlier by everyone. Then number two, adjust and fix the mass of the pendulum to 0.5 kilogram and check the buses for roller and stopwatch. If this has been done earlier, there's no problem. So this is the mass, adjust it to 0.5 kilogram and fix it there for this phase of experiment A1. Roller and stopwatch needed and also activated. Then set the length of the pendulum L to 1.0 meter. Then oscillate the pendulum through a small displacement angle and record the time T1 for 30 oscillations. Okay, using the stopwatch. This time around, you go through. I've just recorded for 10 oscillations, but in your own case, you're recording for 30 oscillations. And once you have taken that one, that is your time T1, record it down. Then repeat step 2. No, repeat step 3 and record the time T2 for 30 oscillations. So you have done, for the first one here, you have done T1, then come over here and do T2 again. Then reduce the length of the pendulum L in step of 0.1 meter and repeat step 2 and 3. Now, let me quickly correct this. Now, I haven't done step 3 here. Please listen to this very carefully. I haven't done this step 3. You have recorded for length, which is 1.0 meter. You have done it twice by recording T1 and T2. Then we are reducing in step of what? Reducing in step of 0.1 meter. So meaning I will do for 0.9 and I will record T1 and T2. Then I will also do for 0.8. I will do for T1 and T2, and I will keep reducing until I have a table that looks like this. So I have 1.0, then up to 0.5, then I will populate these two columns from my experiment. And once that is done, the average time is talking about T1 plus T2 divided by 2, and that will be computed for each of these. The period of oscillation will be equal to T, capital letter T is equal to small letter t divided by N. N is 30 that we have used, and whatever T is here will be used to divide, will be divided by 30, and that gives us this. Then the log will be taken, and the next stage is to plot the graph of log T against log L, ensure the choice of a sensible scale. Then what is the slope of your graph to be calculated? If the length of the pendulum is increased by a factor of 4, how will the period change? Well, why do you use a large value of n, that is 30, and not 5? So give your reason why was it necessary to take log in equation 3 and not and plot log T against log L rather than plotting T against L. Explanation for that. And then what will be the effect of plotting T against L? Then what is the intercept of your graph? So all these are what is to be done in A1. Then quickly let's go to part A2. Now, in part A2, we just come up with the same equation, but this time around we have dropped L. So we are bringing up M. So we have T is equal to E M P. Okay? This is supposed to be equal to T is equal to E M P. Okay? Where here is a constant, and taking the log of this equation will also give us log T is equal to P log M plus log E, where this is also Y, this is X, this is slope M, and this is intercepts. Okay, so I haven't done that. Then we also see the procedure, launch the FET sim, and this time around we are fixing the length of the pendulum to 0.8, and the stopwatch and the roller is also active for us to be able to see and use. Then set the mass of the pendulum to 0.2 kg and oscillate for 30 oscillations and measure T1. Once that is done, repeat that same procedure in 3 and then record time T2. Once that is done, then increase the mass of the pendulum M in step of 0.2 kilogram. In step, this time around we are increasing, so we are to use 0.2 kilogram. If we are increasing by 0.2 kilogram, meaning the next one will be 0.4 followed by 0.6, and the time T1 and T2 will also be taken respectively for the two. And once that is done, then you come up with a table like this for your result and compute every other missing parameter like you have done earlier. And once that is done, you also go ahead and plot the graph of log T against log M and answer the questions that follow. And then you can provide your conclusion based on what you have gone through. I believe with this a simple explanation, you can actually go ahead and explore the beauty of PHY interactive simulation using Pendulum Lab to verify the period of oscillation of simple pendulum. Thank you.